Hi, my name is Connor Bush, and this is my presentation on how to model the Antoine equation given a set of data with both linear and nonlinear regression. So first, we're going to go to Google Colab because that's where we're going to do all of the coding. So we'll just open a new notebook here. So the data that we're using is derived from this set right here. There's two columns. There's the temperature of the water in Kelvin, and then the pressure here in this column. And then we are also given this comma-separated value file with all of the data. So here's the temperature, and then here are the vapor pressures of the water. So what we're going to do first is we're going to copy and paste this link in so that we have it. And that saves the that comma separated values into this notebook. We have to import a few modules first. We're going to import NumPy. We're going to start with the nonlinear regression, so from SciPy, minimize, import, minimize. And then also for the plotting, from I believe it's subplots, import, make subplots. So all of these should be good. Okay, we have a problem. Oh, I misspelled this here. So we should be okay. First we're going to grab the data. We're going to call it data. And then we're going to do load text. So here it's called water vapor pressure.csv. And then since it's comma separated, we have to use the delimiter and set that equal as a comma. So here, if we just look at it, it's an array where the temperature is in this first column, and then the second column is the vapor pressure. So we're going to be using the Antoine equation, which is here. It's the log base 10 of the vapor pressure, and that equals a constant A minus a constant B over a constant C plus T. So just initially, I can get rid of that tab. So the temperature will be just data, and then all of the rows, and then the first column, which would be 0, and then we're going to just say log P, and then immediately just take the log. So of data from all of the rows, and then the first column. So then if we just say, what does this look like? It's here. And then what do the temperatures look like? It's here. So now let's plot this data so we have a visualization of it. So we'll just say fig equals make subplots, and then we're going to have one column and then one row, and then make add scatter. So our x is going to be equal to the temperature, and our y is going to be equal to the log P. Our mode is going to be the markers, which are just would be the data points, and then the name is, we'll just call it data. I think we might have a problem here. I don't remember if that's completely correct syntax, but we'll see. Okay, so that looks good. We're going to update layout, and then we're going to say the width, we'll have it equal to, we'll say 800, and then the height, we'll just say 600. Okay, so here we have this kind of curve being modeled by these, or I wouldn't say curve, it's just the scatter plot. We know this is accurate because around 370 Kelvin, that's the boiling point for water, and that's around 10 to the 5th pascals. So the log base 10 of that would be 5. So this curve this data looks relatively correct. So now that we have this, we can start doing some regression. So I will turn on my iPad here. I have this right here. So essentially what we're looking at is we have these points kind of like this, and then we're going to ultimately want a curve that fits that, and to minimize these deviations here, because that's what a regression line is. It's to optimize the best fit line so that the deviations are as small as possible. We're basically going to sum all of the differences, so that would be log p minus, and I'll just write the Antoine equation up here, so log p equals a minus b over c plus t. So then we're just gonna, I'll just take this and put it down here. And because we have some positive and negatives over here, on here, we're going to square the differences so that everything's positive, and then this is what we call the sum of squared errors, and this is the function that we will be making and optimizing in Python. So if we go back to Google Colab, we're going to define SSE with a parameter v where a, b, and c, we're just going to unpack that. So that's the 3 parameters, and then it's going to return, we're going to do the sum of, so we're going to have log p minus, this will ultimately be squared on the outside here, so we're going to have a minus b, parentheses here, divided by c plus t. So let's see if the parentheses match up. So we have 1, 2, 3, and then 1, 2, 3. So that should be correct, but we will see. And then what we're doing is we're going to minimize SSE, and then we're going to have to do 3 guesses because we have 3 parameters. So I'll just say 1, 1, and just 1. So here, based on our guess, this array here is A, B, and C, and it's noted under X. So if we can set this, we can just say A, nonlinear, B, nonlinear, C, nonlinear, and then assign this to here, and then do .x. So that should assign all of those correctly. So let's just say we want to see what these look like. Here. So then we have these values here. So now that we have the coefficients, we can plot them on here on this graph. So fig.add scatter. So our x is going to be the temperature still. Our y is now going to be a nonlinear minus b nonlinear divided by c nonlinear plus t. And then mode, it'll be lines now because this will be a curve. And then we'll just call this one our Antoine non-linear. So let's see what this looks like. Okay, so as you can see, it's sort of connecting line segments between the different data points. So a way we can fix that, or make the curve a little more smoother, is adding several different data points other than these ones here, because temperature is the independent variable, so we can calculate the different vapor pressures based off of that, and it would still fit within the curve. So we can do this. So we'll start from the lowest temperature value up to the max, the highest temperature value, and then we'll say we'll do 100 data points. So then now we'll be plotting this updated range of x's that we call t-plot. And as you can see, the red line was more just line segments, and now this is a smoother curve. So we can restart and run all, so that we only have one nonlinear regression curve here. Okay, so awesome. Looks good. So that's our nonlinear regression. Our linear regression, I will bring my iPad back out. So essentially what we're doing now, we have to modify the Antoine equation. So originally, it's this. So what we're going to do we're just going to use algebra to manipulate this equation so we can eventually put it into matrices and then multiply that out. So to start, we're going to multiply by c plus t. So then over here we have c log p plus t log p equals a t plus a c minus b. And then we're going to transform this a little more, so we have t log p equals at minus c log p. And here, these are all the constants. We're just going to call this d. So d equals ac minus b. And then eventually, when we calculate d, we'll have to rearrange and then recalculate b. But that's just ac minus d, which we will do later. So then we'll just say plus d. So now we can put this into a sort of matrix form. So over here, looking at the different coefficients, so we have this constant a with t, this constant c with negative log p, and then this constant d with just 1. So we're going to say t1 and then negative log p1 and then just 1. And these are just the different variables that are going with the constants. So then this will be an n by 3 matrix because it'll just go down to t sub n, negative log p sub n, and then just 1. And then we're going to be multiplying this by our constants a, c, and d, and this should come out to have t1 log p1 all the way down to t sub n p, or my bad, t sub n log p of n. So we're multiplying an n by 3 matrix by a 3 by 1, a column vector. So we can multiply because the dimensions match, and it'll come out with an n by 1. So let's call this matrix here, let's call this one, this is our design matrix, we'll call it x. This is our column vector with the constants. We'll call this v. And then this is also a vector, but we're just going to call this y. So basically we're doing the design matrix times the vector with the constants equals a vector with our temperature multiplied by the log of the vapor pressure, and that's just because we had to modify the Antoine equation so we can get into this form. So what we need to do to manipulate to get this vector v by itself, we're going to have to multiply the design matrix by its transpose, so it can be it can turn into a square matrix because we cannot take the inverse unless it is a square matrix, and that is the equivalent of this dividing with matrices. So we're going to multiply by the transpose of x on both sides, and then we can multiply by the inverse of this here. So x transpose times the design matrix, the inverse of that times x transpose times x and vector, and then we have to multiply by both sides with the inverse here. So then essentially this it becomes an identity matrix, which is the equivalent of just multiplying by 1. So this v vector, keep in mind it's a, c, and d are constants that we're looking for, equals all of this right here. So I'll just put this back here again. And this is exactly what we want to put into our code to get the 3 constants. So let's go and do that. Put the screen back. So first we need to make our design matrix we called x. This equals, we have to concatenate, and then we have, so our first column is going to be the temperature. Our second column is going to be the negative log p, and then we're going to do np dot ones. This just creates a column of ones with the same amount as, we'll just say temperature, but I could have done the negative log p. So let's see if this checks out. Looks good. So remember, this is the temperature in Kelvin, and this is the negative log of the vapor pressure, and then there's just the ones, and these correspond with the different constants that we're looking for. So this one's connected with A, this one's with C, and then this is with D. So now we can just extract A, C, and D immediately and begin the matrix multiplication. I'll keep my iPad screen up. Put it in the corner here. So essentially what we're doing is we're trying to multiply by this, all of this right here. So we're going to, I'm just looking at my iPad just so I can get everything correct. So we do np.lin alg inverse, and then we're going to do the x transpose, and then in Python, when you multiply matrices, you use the @ sign, so multiplied by the design matrix. So that's just this first part here, and then we're multiplying that by the x transpose, and then we're multiplying it by y, which in this case is up here, rt times the log p. So since these are two numbers, it's not necessarily a matrix, so inside we just do t times log p. So let's see how this looks. Let's see. Okay, and then remember we need to get b, so b equals a times c minus d. So up here, I'm going to just compare compare the different constants that we have, and then we'll just do A, B, and C. And these numbers check out pretty well. They're very close to each other. So now it's just a matter of going back and adding one more curve to our graph. We're still going to use the 100 values of the temperature in between just to make the curve smoother. Our y is now going to be with these updated constants, b divided by c plus t. And then we have to do this as a curve, and then we'll name this one our Antoine linear. Okay. So let's see how this looks. Oops. Okay, so something came out wrong. So A minus B, C plus T. I think I'm missing. No. Okay. So let's see. So looking at iPad, where's my pen? So we have our X transpose times the design matrix, the inverse of this, times the X transpose times Y, which is our T times log P. Oh. It's because we have to use T-plot. Let's see how I did it up here. Okay, A minus B. So something. Oh, yes. So let's restart and run all, because it was just a matter of the T and T plot. As you can see here, it says linear and linear. Okay, so see this red curve? This red curve is the nonlinear. This green is right on top of the red one. So that means both the nonlinear and linear regression derived the exact or close to the same curve. So yeah, thank you for tuning in.